It is our pleasure that we have Professor Yifang Wang give the IAS Distinguished Lecture today. Yifang graduated from University of Florence, spending some time at MIT and Stanford. He went back to Institute of High Energy Physics in China in year 2001, currently director of the institute. Yifang had been working on E plus C minus collision physics, neutrino physics, and in particular the IAS Beijing machine and the physics there. He may be best known for his contribution or leadership to the diabase neutrino experiment. Diabase experiment, you probably all know, measure one of the neutrino mixing angle, the theta 1,3 angle, and it's considered one of the most important experiments in high energy physics in the last few decades, next to the Higgs boson. In fact, Science magazine listed as one of the 10 breakthroughs of the year in science the year 2012. One of the 10. Higgs is number one. So we certainly feel that measuring one of the fundamental parameters of the standard model, or slightly extended standard model, most important, and the fact that the angle is relatively large has clear implications in a lot of physics to come. Professor Wang also is leading other experiments like the Juno experiment, and he is also leading the effort in pushing for the LiDAR in China. Let us welcome Professor Wang.
It's a great honor and a great pleasure to give this lecture, and it is called the public lecture, but it looks like there are very few generic public here, and everybody are particle physicists or accelerator physicists. So if you think it's too naive, too simple, please forgive me. So I was asked to talk about particle physics in China, but I think this topic is a little bit too large, so I'm going to talk about experimental physics, particle physics, and mostly at IHAP. So if I miss something, please don't complain too heavily. So the particle physics in China actually started in the early 80s, and this is really because of the decision by the Chinese government to construct the Beijing Electron-Positron Collider, known as BEPC. And this is actually a very brave move if you look back 30 years ago. And at that time, there are no hydrogen physics or particle accelerator physics at all in the 80s. There were few MEV kind of accelerators built in the 60s or 70s. And nobody had ever kind of idea how a collider is going to work. So when China decided to move forward to build some accelerators, there were big discussions about whether we're going to build a proton synchrotron 50 GeV proton synchrotron machine or a collider. I think everybody understood that the electron positron collider is cheaper and physics-wise it's interesting. But there are a lot of people afraid that this is almost impossible. I mean, building a GeV machine is already difficult, and steering these beams to collide is something impossible. And also you have to take into mind that it is only 10 years behind the speed, so which means that it is a very advanced machine at that time. But nevertheless, we made the right decision, and the BPC was built, and this is the so-called tau charm E plus minus collider. So if you look at the evolution of this machine, this is the year and this is the luminosity. You can see that BPC, when China started to think about The first particle physics machine is start at a very high level. So it's really a big move, and it give us almost 30 years of a physics study space, and this is where we are now. And we maintain this kind of leading position through upgrade of BPC2, and this also give us the possibility to develop the accelerator and the detector related technologies. So IHAP now is a comprehensive research center for particle physics, astroparticle physics with synchrotron radiation, and also spallation neutron source facilities. And we are now not only doing this research by ourselves, we're also serving the whole science community in China. So this is the BPC, the LINAC, the storage ring, and this is the experimental site. So we have a BESS-3 detector mounted here to study the E plus minus collisions. So IHAP today, we have 8 research divisions. We have Dongguan branch, which is constructing now the spallation neutron source. We have experimental physics, astrophysics, theoretical physics, accelerator, multidisciplinary research, mainly based on synchrotron radiation, and also computer center and so on. So we have roughly 1,500 employees with about 800 or even more students, and our annual budget is roughly 1.4 billion RMB. So our program on particle and astroparticle physics can be shown in this table. So we have accelerator-based science, precision frontiers BESS-3, and also we participate other particle physics experiment in the world. And future, we think that this is IRC and CEPC is our future goal. We also participate in the CMS and Atlas, and we have a non-X-ray-based experiments like the underground diabase, and we participate in EXO in the United States. In the future, Juno neutrino experiment. We have cosmic ray experiment on surface, and with the current one in the future. And we also have satellites and also experiment on the space station. AMS, we participate in international projects, and these are the future programs we have in mind. So let's start from BPC. This is actually the starting point of the particle physics in China. The purpose of this machine is to study the ultimate structure of matter. We know that all the hadrons, normal hadrons, are made of 2 or 3 quarks. And the question is, do we have other type of matter, like 4 quarks, or hybrids, or glue balls, and so on? These are all possible ways of making hadrons. And why not these kind of things? Why we have only these 2 kind of normal hadrons? So this is the question we would like to study. And also we would like to study the interactions between the ultimate constituents of matter, which means quarks. So how quarks bond into hadrons, quantitatively by QCD, how you can calculate that. You need the lattice, but to calibrate lattice, you need experimental data. So we are providing data to calibrate lattice QCD calculations, and in the end, we can understand quantitatively how hadrons are made of. And also, we want to understand the quarks, electrons, and neutrinos, how they interact with each other, so-called electroweak physics. So how we do this study, we need the 3 ingredients: A, a theoretical framework, and B, an accelerator, and C, a detector. So the theoretical framework is the so-called standard model. The experimental data can be expanded by the standard model, and we need new data to test it, and also we need to find the new phenomena. And for the accelerator, here we are colliding electrons and the positrons to produce a huge number of resonances here, like GPSI, psi prime, and many other resonances. This is our energy region from 2 GeV central mass energy all the way up to 5. This is our energy range to study. And also we need a detector. So the so-called standard model, it can be simply described by this ingredient, like building blocks of matter, the particles which mediate interactions, and the origin of the mass, the particle which is responsible for that. And this model is very successful, and but still there are predictions to be tested, like the 4 quarks kind of matter or glue balls and many other physics we need to test. And it is known that it's not ultimate theory and rather effective theory. So we need to understand deeply what's behind. For the accelerator, this is our Beijing electron-positron collider. Originally in this tunnel, we had one machine, and later on in 2008, we had upgrade. So we had 2 storage rings in the same tunnel. So this is a reuse of this tunnel with the new design parameters. The key is the luminosity, 10 to 33. And then we have a detector, and this is a new detector we built in 2008, which consists of a beam pipe, a drift chamber, a cesium iodide calorimeter, and the superconducting magnet, muon chambers, and also a time flight counter. So these are all the numbers, and if you read all the numbers, you can see that they are as good as Bell, and all these detectors, and some of these numbers even better than that. And the total weight is roughly 700 tons, and you look at the cost, the $30 million. We were talking about the cost of constructing operators in China, whether this factor 3 is true or not. Well, I can tell you that $30 million, there's a factor 3 here. Okay. So BEST3 is international collaboration. We had many from Europe, from the United States, from China, and also Korea, Japan, Pakistan, and so on. So this is truly a big international collaboration. So I'll give you a few highlights from this experiment. In 2013, we observed the new particles, which is called Z3900. And this 3900 is coming from reconstruction of a pi plus with gypside. Gypside is a neutral particles. So this ZC3900 is a charged particle. Okay? And it decays to gypside, and gypside is known to be consisted by the charm and anti-charm quark. So you can see that this particle must consist of C and C bar. And with the pion, it is charged, you must have a UD. So this particle, for sure, has to be more than 4 quarks. So be able to have a CC bar and a charged UD kind of stuff. So this is actually so-called multi-quarks. Remember that we talk about the motivation for this experiment. We try to find a new type of hadrons, and indeed this is a very good candidate, being a new type of hadrons. So this is actually one of the most important results we obtained after this machine was upgraded in 2008 and 2009. So this actually made a highlight of the year by the Physics magazine, and it is actually selected as the #1 most important results from that year by this magazine. And also it is reported by many other media that year. So we also had many other important results. For example, we observed, in addition, pi plus pi minus with gypside, we observed this one, these new particles go to pi minus or pi plus, go to d star bar, or go to pi h sub c. And you can see this is a pi the invariant mass of charge pi which H sub c. So this is could be excited states of ZC3900. So we have full spectrum, and also we have seen the neutral states of this of 3900 and also 4020. So you see full spectrum of this kind of new particles, and this would help us to understand how the hadrons are made of and help us to understand quantitatively the QCD. We also see many other states like X1870 or X1835 made of pi eta prime, and also new states like 21 and 20 or 2370. These are all from light hadrons, and you see all these kind of new states which we do not understand by then, and we don't even understand now. So there are a lot of new things here, and we still don't understand how quantitatively all these hadrons are made of. So this is our physics motivation to build this machine, and now we got a lot of new information from this machine. So in summary, BPC2/3 is the best facility in the world for the light hadrons and Charmonian physics. It can measure precisely FD, FD sub S, R values in this energy range, and also the tau mass. And we got a lot of physics results since 2009, and we have published roughly 70 papers, and we will continue at the level of 20 papers per year. We will continue to take data for another 8 to 10 years, and we are thinking about what we can do after 2020. So the idea to build this CPC and SPPC is actually a result of more than 8 years discussion, what we can do after BPC2 in China. So we all regard that BPC BEST or BPC2/3 is a great success, and we would like to continue. And of course, funding agencies also think the same way. So the question to our community is what kind of proposal we can get so that we can get this support from funding agencies, and what we can what kind of say new physics or new ideas we can generate so that we can contribute not only to the Chinese physics community, but also for the international high-energy physics community. So thanks to the discovery of the low mass Higgs and stimulated by the ideas of circular Higgs factory in the world, we came up with this idea of CPC plus SPPC configuration in 2012. So basically, you emulate the LAP plus HC kind of scheme. You first build an electron-positron collider to study Higgs boson, and then afterwards, in the same tunnel, you can build a proton machine to study the very high energy physics. So, in the very short words, the scientific goals of this project is first you study E plus A minus at Z and the Higgs resonance peak, and so this becomes a Higgs factory with roughly 1 million of Higgs over 5 years, and you can study the precision measurement of Higgs mass, JPC, and couplings and so on to study, for example, whether Higgs is fundamental or this composite, whether they agree with the standard model predictions and new properties and so on. So many physics you can study it. And also this is a Z and a W factory. You can do very precision test of standard model. And this is also a flavor factory. So you have a lot of B and C and taus, and you can do these kind of studies. And in the stage 2, you have proton-proton collider. So it's a 50 to 100 TeV machine. And you can do direct searches for the new physics, and then you can do a standard model test. For example, you can do Higgs self-coupling studies. So these two machines actually are complementary to each other. This is considered as a precision machines. You can do solid physics, precision measurement, and if you don't find anything new, then you have something after that. So you have a discovery potential. So a combination actually covers almost all the possibilities. So the dream timeline is like this. So we are going to have a pre-CDR by end of 2014, and also we tried to get some funding request. So now you know that we are 2015. But this is not the, we are in China, so it's Chinese New Year. So we hope that, so we will finish by the Chinese end of 2014. And the hope construction and time is 2021 or 2022, and at the end of 20 something. And then we have data taking for 5 to 10 years. And then after that, we have this proton machine, and we need to have something like 20 years of study, and the construction can come, let's say, 20 years from now. So this actually nicely match with the expectation of the technology development in the next 20 years. So the proposed site could be many possibilities, but we have our, one of the possible choices is Qinhuangdao. So it's a nice place, close to the beach, and we got a very good support from the local government. But of course, other possibilities are still open, so this is not decided. So, I mean, many people ask why you do this in China. I mean, China still, at least on per capita, is still a developing country now. So why you do that? So let's take a Higgs discovery as an example, right? It is an effort by more than 10,000 scientists and engineers for more than 30 years, and has a very rich science, technology, engineering, management, international collaboration, culture kind of implications in that. So this is really a great thing, and the whole society, the whole humankind learned a lot from all this effort. And it has a global influence, more than 1,000 media coverage, and it is a big push to the society and also our life. And during the process, we had the invention of www and also the first browser in the world. So this basically changed our human life for the past 10 or 15 years, maybe forever in the future. So I think China should also contribute to this. And in one word, I think if China is able to build such a big machine, it is good for China to be a better member of the international communities. And we should try to get support from our government and also from our society that this is something good for everybody in the world. So if you look at GDP of the major countries, this is Japan, China, and the EU and the United States, and this is a large accelerators in the world. So you can see that we have HC in Europe, Tevatron, KKB, and China has a BPC. You see little dots here? It's not proportional. Okay, we have also ISC. So we believe that the CPC is a good thing that China should do that. Okay, so the current status. We had a conceptual design, and we also had a preliminary cost estimate. And pre-CDR is mostly done, and we are preparing for international review. And after this review, we will release this document to the public. And we have already identified a long list of R&D issues, and we are going to make a funding request to our funding agencies. So things like machine design, optimization, superconducting cavity fabrication and processing, cryo modules, cryo system, beam diagnosis, vacuum pipes, and so on. It's a long list. But if you look at all of them, I think the major issue is here, RF cavity. And this is, you see, we didn't even list, for example, prototypes, so on. I think the main issue actually is fabrication. I think everybody, or most people in the world now knows how to make prototypes. And in IHAP, we already had 4 different kind of superconducting cavity made, and they're all successful. So really, it is a common issue for everybody in the world how to make the mass production of these cavities. So this is our main issue for the R&D. And we already gave some seed money from IHAP to this R&D issue, and we are looking for the government support. So I think in the conclusion is that if you look at all this list, it is very important for the technology development anyway. Even if you are not going to build the CPC, you still have to learn how to build the superconducting cavities. You still have to learn how to build the cryo modules. So you still have to learn all of this for your accelerator technology development. So this R&D is something no lose. And from this list, we conclude that there are no showstoppers for this machine. We should be able to do it. And we are kind of confident that with the help of from the international community and also make this machine being an international machine, we should be able to, the whole community in the world should be able to build this machine. So that's all for this accelerator-based kind of particle physics. Now let's talk about this non-accelerator-based particle physics here. Start from neutrinos. Sorry, this is because of the change of the machine. We have a lot of neutrinos around us, from supernova, galaxy, Big Bang sound reactor, and even our bodies. We emit roughly 340 million neutrinos per day. So neutrinos is extremely important and around us everywhere. And if you look at the fundamental building blocks of matter, we said this before, this is our standard model. Neutrinos is 1/4 of it. So it is extremely, extremely important. And it is very interesting also because the neutrinos are only particles which does not consistent with the standard, completely consistent with standard model, which need to be modified in a way which we don't know yet. And it is extremely abundant, same as photons. So mass is a very crucial issue to the universe. And it is also very important for the formation and evolution of our universe. So we all know that most people in this room knows that neutrinos can oscillate. And if the mass eigenstate of neutrinos is different from the weak interactions, the neutrinos during the flight can change from one flavor to another. And if you write down the oscillation probability formula, electron neutrinos during the flight can change to muon neutrinos with this kind of probability. So you have oscillation amplitude, which describe the maximum oscillation possibility, and then you have a frequency, or the changes over the flight, the probability, the final probability. It is determined by the mass difference of two types of neutrinos, these two types of neutrinos. So you can see that if neutrino is massless, then you end up no oscillation. And if neutrino has a mass, then and the mass is different, then you get this kind of oscillation phenomenon. If you write down the 3 generations of neutrinos, you end up this kind of oscillation matrix. So we all know that neutrinos can oscillate thanks to this, mainly to these 2 gentlemen. And since the 70s and 80s, they did a lot of experiment and discovered that neutrinos do oscillate, and they got Nobel Prize. So from what we know in the beginning of this century, that neutrinos do oscillate and they describe by two probabilities. One is theta 1, 2, and the one is theta 2, 3. And this is solar neutrino oscillation. This is well known as atmospheric neutrino oscillation. So a very naive question, a simple question is how about theta 1, 3? And there are a lot of theoretical predictions, and the numbers can change from 0 all the way up to more than 10%. So why this is important? And it is actually representing a fundamental principle, and it is a fundamental parameter. You have this famous diagram that theta 1, 3 is one out of 28 fundamental parameters of the standard model. So in principle, if you have all these 28 parameters, you can calculate everything of our world. And in addition, theta 1, 3 is important because it tells us the future. If theta 1, 3 is too small, then we are not able to measure the CP phase, and this is actually a big deal. So how you do the theta 1, 3 measurement at reactors? So it is actually very simple. You look at number of expected neutrinos from reactor, and then you measure these neutrinos. You look at ratio. If it's 1, no oscillation. If it's deviate from 1, less than 1, there are oscillations. And this is the formula of the neutrino oscillation from reactors. And if you look at the predicted or expected precision, you see you have roughly 2% from reactor, 2% from background, and roughly 2% from your detector. So in total, you get a few percent. Now, the theoretical predictions at that time, when we talk about this kind of experiment, people believe that this number has to be less than 1%. Okay, the level of understanding at that time is that these numbers should be less than 10%. So people say, okay, next generation experiment, factor of 10 improvement, so 1%. So if this is 1%, then you see the precision here is 4%, so you need to improve by roughly a factor of 10. So you have to design your experiment with the improvement of the precision by a factor of 10. So how you do that? So this is the layout, and this is diabatic reactor, Ling-Ao reactor, and the Ling-Ao 2 reactor, all the 6 reactors. So we built 2 experimental sites here, and here we call the near site, and then we have far site. So you have a near and a far kind of configuration, so you can cancel out correlated systematic errors. So for example, reactor-related systematic error is largely canceled out. And if you build your detector identical, then many of the detector-related systematic error will be canceled out. So this is one way. And then another method you use to reduce the uncorrelated systematic error is to build multiple modules at each detector site. So we have 2 detector modules here, 2 here, and 4 here. So in this way, the systematic errors of uncorrelated one are reduced by number of 1 over square root of n. So this you can reduce by factor 2 and another square 2. So, and then we have a background, and the background is very much depend on your veto efficiencies or veto efficiency uncertainties. So to make sure your veto efficiency uncertainties are controlled at the level of less than 1%, say 0.2%, you need multiple kind of muon detectors. So if you can imagine that the muons are measured in this way, they are measured 3 times. So by doing this, you can control your systematic error of cosmic muons to the level of 0.2%. So this is again another factor of 10 improvement over the past experiments. So by doing all of this, we managed to reach the desired sensitivity and or systematic errors. So this is again a large international collaboration. We have 16 from the United States, 2 from Europe, and many from Asia. And this is actually the first large scientific collaboration in China, between China, Taiwan, and Hong Kong. So we started the experiment, proposal of this experiment in 2003, and we managed to finish most of the civil construction in 2010. So actually the project got approved in 2006. Then we had detector construction, and by the time of August 2011, the first detector is running, and end of 2011, the fire detector is taking data. So this is almost 8 years of preparation and construction. So you see these 8 gentlemen standing here, and each one contribute to at least 10 million RMB to this project. So this is the underground laboratory. We have this surface entrance portal here, and we're going down, and this is the first experimental hall. We call it Hall 1. And then we go in further, and this is a Hall 3, the far hall, and this is a Hall 2. So you see we have these 2 near detector site, and this is a far detector site. So the total tunnel length is about 3 kilometers, and we have 3 experimental hall, one hall for water, and another small hall for the liquid scintillator. So we had roughly 3,000 blasting right next to reactors, and this is one of the major issues we had for the safety of the experiment. And the closest distance to reactor is 400 something meters, and it's a big solid rock. So vibration is very easily propagated to the reactor cores. So this is actually a major issue that we managed to successfully control everything. So this is the detector installation, the water pool, phototube structure, and the reflector. This is made of Tyvek, water pool, and the fully filled detector modules. This is 100 ton each, was installed into the water pool, and then you put the water in it, and you put the cover, which is light sealed and also gas sealed. So by doing this, you can run your experiment with light on. So phototube is inside. So this is actually not easy job for this cover. This is a detector, stainless steel tank, 5 meter diameter and 5 meter height. You have bottom reflector to improve or to increase the photocathode coverage to get more light from the scintillator. You have 4 meter aquatic vessel, 3 meter aquatic vessel, phototubes, and then you put top reflector, and then you put the cover on it. You make sure there's no leak because the detector is sitting in the water 2 meters under the surface. So this is actually a big issue to build this kind of 5 meter diameter O-rings. This is not easy. This is the experimental hose. You have RPC on top, and underneath this RPC, we have this water pool and the detectors in it. So after something like 55 days of data taking, we managed to see that indeed there is a neutrino deficit, and we get something like 6% less than what we anticipated. So you can see that we designed the experiment for 1% sensitivity, and we ended up at 10%. So this is really a big surprise, and that's why instead of 3 years running for 50 days or 55 days, we get our first results. And you see that this deficit appears at the peak of our energy spectrum, which shows that indeed the disappearance only happens here, not here, not here. So this shows that it is consistent with the oscillation. And this is certainly on purpose that we design our experiment with the right baseline so that the disappearance happens at the peak of your spectrum. So we got a lot of media coverage, and over the last 2 or 3 years, we still improving our results. So this is our first paper roughly at 20% uncertainty, and now we are something here at 6%. So this is more than 20 sigma, kind of non-zero determination of theta 1/3. And of course, there are many other experiments had similar results. Some are a little bit ahead of us, but with 100% kind of or 80% kind of precision, and we are actually get the best results in the past few years. So why it is so interesting? You got a lot of media coverage and so on, and a lot of people talking about that. My understanding is that there are some surprises here. First, that neutrinos do oscillate in a normal way. There are no new symmetries, because theorists were talking about new symmetry that this number equals to 0. And actually a lot of model builders believe that this number should be very small or very close to 0. But indeed it's not, it's very big. But from point of view of normal people, say non-theorists, I would say this is a normal way. So you see this number here. But on the other hand, there is a big surprise, because this number is factor of 10 larger than what most people anticipated. So this gives us also a lot of hope that we can measure CP phase and the mass hierarchy immediately now with nowadays technology. So that's why everybody got excited and everybody moved quickly to design their own experiment to measure the mass hierarchy and the CP phase. So if you look at what we understood now for the neutrino physics, we have a long list of unknowns. And among these unknowns, I think some of the most important question is what is the neutrino mass hierarchy and what is CP phase? So we come up with the idea that we could measure the neutrino mass hierarchy and the unitarity of neutrino mixing matrix by a new generation of react neutrino experiment. So this is called Juno, and the idea is to use react neutrinos from these two reactor complex, and you look at the equal distance, you build your detector here, so this kind of detector. And if you look at the power, and this is actually the largest nuclear power complex in the world. The two reactors give you roughly 36 gigawatt. Okay, this is a really big thermal power. And this is the side of the detector, which is right at the oscillation maximum of theta 1/2. So by place your detector here, you can actually measure the neutrino mass hierarchy. So the physics which you can imagine is the mass hierarchy, the precision measurement of mixing parameters. You can study supernova neutrinos, gel neutrinos, stellar neutrinos, and solar neutrinos, and many of them. So give you a few number here. If you have a detector with a 20 kiloton target mass and energy resolution is 3% over square root of E, thermal power 36 gigawatt, for 6 years, you can determine the mass hierarchy at the level of 4 sigma if you use the input delta m squared mu mu at the level of 1%. If you don't use this information, you get 3 sigma. You lose 1 sigma because of this. This is kind of paper we published. Another physics you can do is that you can do a very precision measurement of oscillation mixing parameters to a level of less than 1%. You probably know that we have built many B factories, C factories, 5 factories, and so on. But still, for the CKM matrix element, we are at the level of a few percent. But for neutrino physics, very quickly, we can end up less than 1%. And by doing this, by having this kind of information, you can test the neutrino mixing matrix unitarity to the level of less than 1%. So this is actually also a big deal to study the non-standard interactions of neutrinos. Oh, yeah, it has no sensitivity there. basically. Sensitivity is the theta 1.3 is diabase. This is Juno. Sorry, basically it's no sensitivity. So how to build this? How to do this experiment? We want to have a 20 kiloton detector. Okay, so 20 kilotons. So diameter of this acrylic tank is 35 meters. So this is 13-story building made of acrylic. Okay, how you build this? The largest one the previous people built was 1 kiloton. Okay, so we had 2 different designs. This is a requirement. We had to worry about the mechanics, optics, chemistry, and also, most importantly, we should be able to build this detector in say less than 1 or 2 years. Okay, so this is a big challenge, and the current design are the following. So we have a 35-meter diameter acrylic tank with a stainless steel truss outside to support and hold this ball, and we have to worry about all of these kind of issues, and we have another backup option to build a stainless steel tank. Everybody believes that building the 35-meter diameter stainless tank is easy. Okay, everybody, I think most people can do it, but then we need to build acrylic kind of panel to support a balloon, because the phototube in this option mounted on the stainless truss, and this one is mounted on the stainless steel tank. So you have to be able to see through into this liquid scintillator. So this balloon has to be transparent. We have to worry about the leakage. I mean, the balloon could easily leak, and you have cleanness problem and deployment and so on. A lot of problems. So this is actually a big challenge, and I think we have some ideas now, and by mid of this year or maybe end of this year, we are going to decide which option we are going to move forward. Second challenge is the liquid scintillator. Okay, so up to now, the largest liquid scintillator people have been made of is the 1 kiloton kind of detector. So now this is 20 kiloton, factor of 20. And the transparency of the liquid scintillator, the best one up to now is 15 meters. And now we have to make 30 meters. So you need a factor of 2 improvement. And so you have to worry about many things, a long list of R&D and so on. And the key is try to purify your liquid so that you can reach this kind of transparency. So we had R&D, and we now reach something like 25 meters, so very close. And we believe that in the end we will be something around 25. It should be feasible. The third one is the high quantum efficiency phototubes. We all know that most of the phototubes in the last 20 years are made from Hamamatsu. But when we started this 5 years ago, the quantum efficiency of phototubes are typically 25%, and we hoped for 35%. So we started to develop our own phototubes to get something like 35 to 40% quantum efficiency. So this is our R&D. We had a group of industry people and also ourselves. We decided to use a microchannel plate in this phototube in place of diodes. So this is a kind of way to improve the final collection efficiency. So we had basically now 3 choices of phototubes. One is our own development of microchannel plate PMTs. We can buy Hamamatsu, because Hamamatsu now is SBA kind of photocathode. Starting from last year, they can produce 20-inch phototubes with the 30% quantum efficiency. We also have another company in China which bought photonics from France, and now they are built their production lines, and they can produce 8-inch tube and 12-inch tubes. So we asked them to work on the 20-inch phototube, and they are doing it now. So we had some progress with our own phototubes. Most technical issue has been resolved in the last 5 years. And we made many 8-inch, 20-inch prototypes. So this is one of them. You see this is a 8-inch, 20-inch. And this is the numbers. You see these two are Hamamatsu, the normal photocathode, and this is SBA photocathode. So they are talking about 25% or 30%, and we manage now to reach roughly 25%. And with all these numbers, very similar to Hamamatsu phototubes. And this is a single photoelectron peak. You can see very nice single photoelectron peak. And the peak-to-valley ratio is more than 3. So we are in reasonable shape, but the major question is whether we are able to produce 20,000 phototubes with the same quality.
The rise time is 5 times as good. Is that important?
Not extremely important. It has some advantages, but not the key factor. The fourth challenge is the civil construction. Okay, so we need to build an underground cavern, 50 meters diameter and 70 meters high. This is actually the largest underground cavern in China, at least. And how to build this is technically feasible, but practically we all know that civil construction is a big issue, and always you delay, you over your budget, and all kind of troubles you may have. So we need to build a slope tunnel, 1.3 kilometers, then a vertical shaft, 600 meters, and then we get access to this underground lab. This is the shape of the lab, and this lab is underneath of a little hill with 200 meters of 270 meters of rock above the ground. So the total overburden of this underground lab is roughly 700 something meters. So it's 600 plus 200, and you dig 80 meters, you lost 80 meters, so it's 700 something overburden. So this is our surface lab. We have a assembly building, and then the tunnel going down. And this is our scintillator purification factory, and then our assembly building, control rooms, dorms, and so on. So this is the current schedule. We prepared for the civil construction the last 2 years, and last week we had the groundbreaking ceremony, and civil construction will be, this is 2015 to 2017, 3 years. And the detector component production will start next year, and the installation will be starting from 2018 to 2019. And hopefully we can start data taking on 2020. So this is the big, again, a big international collaboration. So we have many from Europe, from United States, and also many from Asia. We have now more than 300 collaborators, and we believe that we may grow up to something like 500, I think, in the future. So that's all for the neutrino physics. Now a few slides for the cosmic ray physics and also satellite kind of space experiment. So we have been working on the cosmic ray physics in Tibet for the last 20 years. And actually, starting from 50s, I have been working on the cosmic ray physics. So we have a big team for a very long time. We are talking. This is the Tibet experiment, ARGO, in collaboration with INFN, and this is AS Gamma in collaboration with Japan. So we think that we need, this is from 90s, so we think that we can build a much larger air shower observatory with 1 kilometer kind of diameter. And you can do cosmic ray physics to measure spectrum and the composition of individual pieces over 2 knees, so you can understand the origin of the cosmic rays. And also you can do a gamma ray astronomy. It is very much complementary to the CTA in Europe. So this is sensitivity curve of CTA as a function of energy, and this is a lasso. So you can see that it has a better sensitivity at higher energy, and also it is good for the time variant and the extended sources. This is the pointing devices, and this is actually is available. It's the all sky survey, so you have a very good coverage of the sky, and also it is there all the time. So even if the source is variant over say a year or maybe a month, you can see very clearly the variation. And we have also many space satellite or space station kind of space program. The one we are now constructing is the Xray Telescope. This is going to be launched in 2016. Sorry, this again, like many other projects, we have delays. So one more year delayed. And this is actually the largest scientific satellite we ever built up to now. And then we have a collaboration with Switzerland, gamma ray burst polarization measurement called the POLAR. This is again 2016. Then we have, in collaboration with France, a satellite called the SWARM. And of course, we are also members of AMS. The next generation kind of space program we have in mind is a calorimeter in space called HERD on board of Chinese space station. And the Chinese space station is going to be launched in 2020 or maybe 2022. So we think that we can build a detector on that space station as the next generation kind of detector after AMS. So the science goal is to detect or search for dark matter, look for gamma ray lines from 0.1 to 10,000 GeV. It can measure the spectral and the composition of cosmic rays between 300 GeV and 1 PeV. And it is actually complementary to LASSO. So you can actually calibrate your underground, your surface measurement with this direct measurement device up to the level of 1 PeV. So this is a way to study the cosmic rays in a very direct way. And it can improve the acceptance by a factor of 10 over Fermi, AMS, DAMP, and CREAM, all the other space experiments. You can see that the acceptance factor is 3 point something, and this one the point something. So factor 3 to 10. And this is because this detector, this calorimeter used in RYSO crystals is isotropic from all the directions. So you can actually get cosmic rays from all the 5 directions, and they can have exactly the same kind of capabilities to all the directions. So that's why you can increase the acceptance. It is already selected by the Chinese space station office, maybe. Some committee of the space station science program. They selected this as one of the top mission for the future. It is going to be a collaboration between China, Italy, Switzerland, Sweden, and so on. And we hope we can launch in 2020 something. Okay, so IHAB is also doing many other things to service the community. For example, we are now constructing the Chinese spatialization neutron source in Dongguan, not very far from here, I think 100 kilometers from here, or maybe less, 60. So the phase 1 is 100 kilowatt, and the phase 2 is 500 kilowatt, and the expected completion time is 2017. So this is a picture of some time ago. We're also working on the R&D of accelerator-driven subcritical system. So these are the accelerators, inject the proton beam to a reactor. So IHAB is responsible for this part, and maybe in the future a little bit some part of here. So we are working on the accelerators for this project. And we are also working on the light source. So this is a BPC. This is a dual-purpose machine. And every year we have roughly 3 months of synchrotron radiation operation. And in the future, we would like to build a new light source we called high-energy photon source. And this will be a circumference. It's not a project being proved, so we are still working with our funding agencies to get this project approved. Okay, so this is a summary of all the larger projects at IHAB. We have Diabase, Juno, BESS-3, and we hope we will follow the BESS-3 by CPC and the SPPC. And then we have a cosmic ray experiment, satellite, and then the light source and neutron source future. So this all the way go to the 2050 or something. Hopefully it works this way. So summary, we hope we can build a world research center in the next 10 or 30 years. So thank you very much.
That was a very impressive summary. Now, I want to go to the very beginning. Even what you already accomplished with BESS-3, even that very soon BEL 2 will start, what are the key targets of the next years of operation of BESS-3? Are there things which are just improvements, more precise measurements, or there is some clear new topic that can be addressed with that additional luminosity?
This is a very critical question. Yes. When we designed the BESS-3 experiment, we had a list of targets. And up to now, I think from a point of view of integral luminosity, we're still missing, say, 9 billion of chip size. We're still missing something like 20 inverse femtobar of psi double prime for precision measurement of electric weak parameters. And we also have to do a precision measurement of tau mass. And we did already some R scans, and we are working on this first batch of R scan data. And maybe in the future, we would like to improve at the lower energy, the R values. So I think the big chunk of luminosity we missed up to now is the GPSI, which is 9 billion GPSI events, looking for glue balls and so on. But I think the difficulties is not the machine, it's actually the physics analysis method and so on. So the partial wave analysis, how really you can understand the glue balls from a normal meson and so on. So it is a combination of analysis techniques and also the theoretical understanding of QCD glue balls and so on. So further improvement of statistics of GPSI is not absolutely clear at this moment how we can gain on the glue balls. So that's why we want to study it and wait a little bit to move to JIP side to get more statistics.
So Yifang question, this the Chinese high physics community is relatively small. To build, operate and CPC, you probably need to build up the community. Can you comment on that?
Certainly, the current community size is not large enough for CPC, and not even mention the SPPC. But I think in the next 10, 20 years, if we set this goal, and if we get support from both the funding agencies and also the whole science community, we should be able to expand. And at the level of 10% kind of growth rate for the next 10, 20 years, we should be able to get to the size that we hoped for. So we had the calculation, and by the time of 2035, if we keep the growth rate of 10%, we should be there.
That growth rate is not just from IHAP. I assume there's a lot of new universities going to join.
Yes, of course.
I can shout.
Okay.
So just following on from that, I thought I saw ILC on your original plans, that it didn't turn up in any detail. Where does it fit in?
Well, I did not talk about every project. I talked mostly, say, I have hosted projects. The IRC is one of the major machines we have been talked about for the last 20 years, and I think it still remains to be a key project for our future. So we fully support IRC, and we hope it can get through. And if it is approved by the Japanese government, we would like to participate as one of the major players.
Don't you think there's quite a conflict?
No, I don't think so. I think it's easy to sell to our funding agencies that if you don't support IRC, you will not get support to the CPC from international community. So if you sell it as one package, it's probably easier. But if you sell it separately, you may end up troubled.
I've got a question about what are the major funding agencies in China? Because in the US it would go through Congress and the DOE, and in Europe it goes through sort of CERN as an international body. So when you refer to funding agencies, what would be the ministries or the councils that would be?
We have many funding agencies. That's also one of the reasons we are able to get so many projects. So this one, for example, we got from 6 funding agencies in China, so that we are able to build the database so quickly. We get a little bit from each of them. And Juno is from Chinese Academy of Sciences. This is from the central government, and we hope this is going to get from central government. This is from Ministry of Science Technology, and this is maybe from central government, and this is from a space agency, and hopefully these were also from space agency, and so on. So a little bit from everywhere.
Okay, so let us thank Yifang again.
Thank you.